Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know about probability for the exam. So we're going to start by defining a random variable because probability is all about random variables. We know what a variable is. A variable, which we usually give a pronumeral, a letter, is just something that can take different values. What makes it a random variable is that the values it takes are determined by chance. So we use capital letters for random variables and small lowercase letters to indicate the values that they actually take. So we are looking in this section at discrete random variables. And what makes a random variable discrete is if it can only take a finite number of values. For example, if the random variable can only take, say, values that are whole numbers, it is discrete. So just to give you an example, if you roll a die and let x be the number that's rolled, x is discrete. Because if you roll a die, x has to be a whole number. 1, 2, 3, 4, 5, 6. It can only take a certain number of values. If, for example, I pick someone at random and let x be the time they take to run 100 meters, x is not discrete. The reason being, if I time how long it takes someone to run 100 meters, it could take them 9.1 seconds, 9.11359 seconds. X could take infinitely many values. It could take really any value between like 10 seconds and a minute, depending on the person, but it doesn't have to be just whole numbers. The time taken can be decimals. That's why this is not discrete. We're only looking at discrete random variables. So we're going to start by looking at probability distribution, and that's just basically where you have a table like this or a formula that tells you how to calculate the probability that x, the random variable, takes different values. So here in these tables, little x, as I said, lowercase letters are the values actually taken, and px, or written like this, prx, that means the probability that the random variable takes that value. So the random variable here, the probability it takes value 1 is 0.2, probability it takes the value 2 is 0.4, and so on. So to make these probability distributions valid, two things need to be true, which you probably already know. Firstly, probabilities must always be between and including 0 and 1. And secondly, all the probabilities must add to 1. Probably already knew that. Both of those must be true for the probability distribution to be valid. So for example, this probability distribution is not valid. Even though each probability is between 0 and 1, if you add up all these, they add to 1.1. They don't add to 1. In this one here, the probabilities add to 1, but we have a negative value. You can't have a negative value for probability. It must always be a number between 0 and 1. So this is not a valid probability distribution. This one here is a valid probability distribution because if you add up all the numbers, you get 1, and each probability is between 0 and 1. This one here is also a valid probability distribution. This is a special type of probability distribution called the uniform distribution. Uniform means that each of the values that the random variable can take have the same probability. So you can have a uniform distribution where there are 5 possibilities or 6 possibilities or whatever. They just have to have the same probability. So both of these are valid probability distributions because all of the probabilities are between 0 and 1 and all the probabilities add to 1. So let's now look at the mean and variance of a probability distribution. So the mean or expected value is written like this. This means expected value of x. Capital X means a random variable, and it basically means if we perform the experiment over and over again, what would be the mean of all of the values we realize? That probably sounds a bit confusing. So let's look at an example. This is actually the probability distribution you would get if you rolled a normal 6-sided die. So this is actually a type of uniform distribution. Now, to find the expected value, what we do is we take each possibility, multiply by its probability, and then add all those together. So here, the expected value would be 1 times a 6th plus the next number times its probability plus the next number times its probability, and so on. So if you add up all of these, the number you get is actually 3.5. See, that sounds really weird because you can't actually get that. If you roll a die, you can't actually roll 3.5. So how could the value we expect be 3.5? Well, what this value is saying is if you rolled a die over and over and over again, and you took the mean of all of the numbers you rolled, we expect that it would be 3.5. So the variance is a related concept, but the expected value measures like the center of your data, what you expect to happen. The variance is a measure of spread. It measures how close to the expected value something might be. So the lower the variance, that means that if we perform an experiment over and over again, the mean will be close to this expected value. Of course, if I roll a die over and over and over again, there's no guarantee that the mean of all of the numbers I roll will be 3.5. Could be 3.4, could be 4.1. We don't know. The variance indicates whether or not it's likely that when I roll a die heaps and heaps of times, the mean will be close to 3.5. So the lower the variance, the less likely my observation is going to deviate from this. If I have a high variance, it's likely that my scores, if I roll a die over and over again, will be very different from 3.5. So this is how you calculate the variance. You take the expected value of x squared and you minus the mean squared. So let's find the variance of this distribution here. So we need to calculate the expected value of x squared. So we're going to add another row here to our table. So that row is just going to have x value squared. So 1 squared just gives you 1, 2 squared 4, 3 squared 9, and so on. So we're going to calculate the expected value of x squared very similar to how we calculated it here. We take each score for x squared and multiply by its probability. Each value for x squared and multiply by its probability. So if I put all of this on my calculator, the sum of each score for x squared times the probability, then I get 91 over 6 or 15 1/6. So that means that the variance of x here is just going to be the expected value of x squared minus the expected value of x, the mean, all squared. That's how we calculate the variance. And so the answer I get is 2.916 recurring. That's the variance. So to find the standard deviation, we simply square root the variance. That's what this formula says here. Standard deviation of x equals the square root of the variance. So in this case, where x was the number that I roll when I roll a normal 6-sided die, the standard deviation is the square root of this, which is about 1.7, just to one decimal place. So that means if I rolled die over and over again and then I calculated the mean of all my scores, let's say I did that heaps and heaps of times. On average, just average, my mean that I calculate when I perform the experiment will differ from this by about 1.7. That's what the standard deviation is supposed to mean. All right, let's now move on to combinations. So we actually looked at combinations last year. They are just counting tools. They help us count things really quickly. So this formula tells you how many ways you can choose R objects from a group of n, and they are really useful in probability. So let's do this question. I need to pick a team of 7 players from 8 year 12, 8 year 11 students. What's the probability I pick all year 12 students? So probability follows this really simple formula. The probability of an event is the number of ways the event can occur over the total number of outcomes. It's NS for number in sample space, because sample space is a list of all possible outcomes. So combinations can help us calculate this number and this number. So firstly, how many ways can I pick all year 12 students? Well, what I'm doing is I'm taking a group of 8 Year 12 students and picking 7. So that's the number of ways I can pick Year 12 students, the number of ways the event can occur. The total number of outcomes, there are 8 Year 12 and 8 Year 11, so 16 students to pick from, and I'm picking 7. Now, both of these numbers can be calculated in your graphics calculator. You go math, and then you scroll over to the probability menu, and you click the NCR button. So you should be able to see 8C7 is 8. There are 8 ways to pick the students, but there are 11,440 ways to pick 7 students from 16. So this is the required probability. It's about 0.0007, so you can see it's very low, but you can see the question was made so much easier using combinations. All right, let's now move on to Bernoulli trials. So we're going to start with a random variable x. So if x is the result of an experiment, and x can take 2 possible values, 0 corresponding to failure, 1 corresponding to success, then we say x is a Bernoulli random variable and write it like this. P is just the probability of success. So that might not make a lot of sense. So let's look at these 2 random variables I've called x1 and x2. Turns out one of them is a Bernoulli random variable, one is not. So let's say I again roll a normal 6-sided die. So if I let x1 be the number rolled, see x1 can take 6 values. x1 could be 1, 2, 3, 4, 5, or 6. So it cannot be a Bernoulli random variable. It's still a random variable, but it's not a Bernoulli random variable because I said a Bernoulli random variable can only have 2 possible values. 0 for failure, 1 for success. However, this random variable, x2, is a Bernoulli random variable. So if I let x2 here, this random variable, it will take the value 1 if the number I roll is a 6. It will take value 0 if the number I roll is not a 6. That's what a Bernoulli random variable looks like. In this case, rolling a 6 is like our success, and rolling something other than a 6 is like our failure. So if x is a Bernoulli random variable, the expected value of x is just p. So if 1 is a 6 rolled, the probability of rolling a 6 is 1 over 6. So here, the expected value of this random variable is 1 over 6. Now, of course, this isn't actually possible. You can't roll 1 over 6 sixes, but this just says we expect that we will roll a 6 1/6 of the time. Every 6 rolls, we expect to get a 6. The variance of a Bernoulli random variable, you just take the probability of success and multiply by the probability of failure. The probability I don't get a 6 when I roll a die is 5 over 6. So that will just be 5 over 36. And of course, if I was asked for the standard deviation of this variable, I would just square root that. So Bernoulli random variables are very important because they're like the building blocks of the binomial, hypergeometric, and geometric distributions. So let's now look at the binomial distribution. So when we perform many, in this case I've just said n, independent Bernoulli trials, we end up with a binomial distribution. So the binomial distribution calculates the probability you get a certain number of successes from heaps of independent Bernoulli trials. So if x follows a binomial distribution, we write it like this. N is just the number of trials, and P is the probability of success on each trial. It's important here, the probability of success needs to be the same from trial to trial. That's why we said they have to be independent. So this is the formula we use to calculate the probability I get a certain number of successes from n Bernoulli trials, and there's also a formula for expected value and variance. Probably isn't making a lot of sense, so let's look at an example. So let's say again we roll a die. This time we're going to roll a die 10 times. So each time we roll the die is a Bernoulli trial. We're going to let x equal the number of 6s. So each roll of the die is a Bernoulli trial, where x equals 1 if I roll a 6, x equals 0 if I don't roll a 6. So we're going to use the binomial distribution to calculate the probability I roll 4 6s. So what we're actually calculating here is the probability that I have 4 successes from 10 Bernoulli trials. So this is how I calculate it using this formula. So it's n number of trials, choose 4, because I want 4 successes. So then the probability of success on each trial is 1/6. Every time you roll a die, you have a 1 in 6 chance of getting a 6. So probability, and the power is the number of successes. But if I get 4 6s, that means I got 6 numbers that are not 6s. So the probability in each trial that I don't get a 6 is 5/6. And I put a 6 there because I want 4 6s and 6 not 6s. So why do I have this number here at the front? Well, that's because there are heaps of different ways that you could get 4 6s. You could roll 4 6s in a row, and then the next 6 trials are not 6. You could roll the first 6 trials I don't get a 6, and then the next 4 trials I do get a 6. This number here actually tells us the number of those possible combinations. So here, each combination is a possible way of getting 4 6s. Each combination is something like, getting 4 6s in a row, then getting 6 not 6s. That's one combination. Another combination is I could get 2 6s, 6 not 6s, and then 2 more 6s. This is just the number of ways that it can happen. The number of different outcomes where I can get 4 6s and 6 not 6s. So putting that on our calculator, we get the number 0.054. So there is a 5.4% chance that if you roll a die 10 times, exactly 4 of them will be 6s. So just to quickly show you what these mean, so EX is very logical. It's the number of trials, 10, times the probability of success on each trial. I expect I will get a 6 on 1/6 of the trials. So here the expected value of X, 10 times the 6th, is actually 1 2/3. It's not a whole number. Again, this isn't actually possible, but that doesn't matter. So the variance of X in this case, it would be N times P times 1 minus P. And so we get about 1.39, and if I wanted to find the standard deviation of X, I would just square root that. Now, I just want to point out that this number here can actually be calculated on your calculator. What you do is you go to the distribution menu and you pick out Binomial PDF. So you have to input the parameters. So there is 10 trials, probability of success is 1/6, and we want exactly 4 successes. If you put this on your calculator, it will calculate the probability for you, which is really, really handy. Now, it turns out there's also another function called Binomial Cdf, and we will now look at that. Really useful. So on the previous slide, we looked at the binomial PDF function. That calculates the probability that you get a certain number of successes. We're now going to look at the CDF function, which instead calculates the probability that the number of successes is less than or equal to a given number. So this is the kind of question for which we would use the binomial CDF function. So let's say I roll a die 10 times. What's the probability I roll between and including 4 and 9 6s? So if I roll a die 10 times, I could get 0 6s, 1 6, 2 6s, all the way up to 10 6s. So really, what I'm interested in is the probability I get between and including 4 and 9 6s. So it would take me a long time to calculate the probability I get 4 6s, plus the probability I get 5 6s, plus the probability I get 6 6s. It takes a long time to say, let alone calculate. But I can use my binomial CDF function for this. Now, I can't use this function to calculate this probability directly, but this is what the CDF function can do. I can get it to calculate the probability I get 9 or fewer 6s. So to do that, I go to my calculator. It's again in the distribution menu, binomial CDF. So here I have 10 trials. Probability of success is still a sixth, and I write 9. This CDF won't calculate the probability I get exactly 9 6s. It will calculate the probability I get 0 or 1 or 2 or 3 all the way up to 9 6s. So if I put this on my calculator, I get about 0.9. There's lots of 9s, and that kind of makes sense because the probability of getting 10 6s is really, really low. So this is the probability I get 9 or fewer 6s. So I can also use this function to calculate the probability that I get 3 or fewer 6s. So to do that, it's just going to be binomial CDF. We've still got 10 trials. Probability of success is a sixth. But this time, I'm finding the probability I get 3 or fewer 6s. So once again, I want to make the point, if I put this as binomial PDF, it would calculate the probability I get exactly 3 6s. Binomial CDF calculates the probability that I get 0 or 1 or 2 or 3 6s. So putting that in the calculator, I get about 0.9303. So, what would be this probability in green? Well, it would just be the probability I get 9 or fewer 6s minus the probability I get 3 or fewer 6s. So, the probability that the number of successes was between and including 4 and 9 will just be this number minus this number. And it is approximately 0.07. So there's only a 7% chance you get between 4 and 9 6s. That sort of makes sense because if you roll the die 10 times, you would only expect to get 1.67 6s, between 1 and 2 6s. So just make sure you're aware here. I know it's a bit counterintuitive, 4 and 9 6s. I did probability of 9, but minus probability of 3. 1 less than this one. And that's because I wanted to include the possibility that I get 4 6s. All right, let's now move on to another type of distribution that's very close to the binomial distribution. So, the hypergeometric distribution is similar to the binomial distribution in that it's also about the number of successes from n independent Bernoulli trials. The difference between hypergeometric and binomial distribution is that the hypergeometric distribution, each trial is performed without replacement. So the probability of success is different in the first trial than it is in the second trial, and it's different in the second trial than it is in the third trial, and so on. So, to calculate probabilities involving this hypergeometric distribution, we're really using this formula here. Probability of an event is the number of ways it can occur over the total number of outcomes. So this is the kind of question for which we would use the hypergeometric distribution. So I need to pick a team of 7 players, 8 year 12, 8 year 11 students. What's the probability I pick exactly 4 year 12 students if players are picked randomly? So this is very similar to the question that we did when we're doing combinations. The question then, though, was a bit easier because we were finding the probability that I pick all year 12 students. This time, it's a bit harder because the probability I'm picking some year 12 students, I need to account for the fact that I'm picking 4 year 12 students, and I'm also picking 3 year 11 students to make up this team of 7. So here I'm going to let x, my random variable, be the number of year 12s picked. So it turns out x follows a hypergeometric distribution. So this picking is without replacement. If you're picking a team of 7, if you pick a guy from year 12, say his name's Ethan or something, if you pick him, you can't pick him again the second go. If you pick Ethan as the first player, you now have only 7 year 12s to pick from and 8 year 11s. That's why this is without replacement. You can't pick the same person twice. So, X follows a hypergeometric distribution with these parameters n, k, and n. What do they mean? N is the total number of objects. So in this case, the objects are people. N is the total sample size from which you have to pick. So in this case, big N is 16 because we have 16 students to pick from. So K is the number of objects with the attribute we're interested. Here, the attribute is being in year 12. So there are 8 students in year 12, so big K is 8. So n is the number of objects that we pick. So from this 16, we're picking 7 players. So little n is 7. And little k, that's what we're interested in. We're finding the probability here x equals 4. The probability that 4 students are in year 12. So little k here is 4. So let's calculate the required probability. So we start off by figuring out how many ways can I pick for year 12 students. Well, there's 8 to choose from and I'm picking 4. But as I said before, if I'm picking 4 year 12 students, exactly 4, that means that I want to pick 3 year 11 students. So how many ways can I pick 3 year 11 students? Well, there are 8 year 11s to choose from and I want to pick 3. So it's just 8 choose 3. Here, of course, big N minus K, 16 minus 8 gives 8, and little n minus little k, 7 minus 4 equals 3, following that formula. So the total number of outcomes, the total number of ways I can pick 7 players from a group of 16 is just 16 choose 7. Big N choose little n. And you can calculate each of these on your graphics calculator. So we get 8 choose 4 is 70. So it's 70 times 8 choose 3 is 56 over 11,440, and that's approximately 0.343. So about a 34% chance you'd pick 4 year 12s and 3 year 11s. So we also have a formula here to calculate the expected value of x. So the expected number of year 12 students would just be little n, so 7 times big K over big N. So 7 times 8 over 16, 7 times a half. That makes sense. Half of the students were year 12. So we expect half of the 7 would be from year 12. Now, half of 7 is 3.5. Once again, the expected value doesn't have to be something that could actually happen. You can't actually pick 3.5 year 12 students. But if I performed this experiment over and over again, the mean of those scores, the mean number of year 12 students picked each time, I expect would be 3.5. All right, let's now go into our final topic of geometric distribution. So the geometric distribution also involves Bernoulli trials and with replacement. So that's similar to the binomial distribution. The probability of success is the same each time. Each trial has to be independent. But unlike the binomial distribution, which finds the probability of a certain number of successes, the geometric distribution finds the probability that it takes you a certain number of trials before your first success. So if it follows a geometric distribution, we write this, where P is the probability of success. So this is very logical. Let's try it out on this question here. So if I roll a die heaps and heaps of times, we're going to let X, our random variable, be the number of the roll on which the first 6 rolls. So if X equals 1, that means the first 6 was rolled the first time. If X equals 2, that means I first rolled a 6 on the second roll. If X equals 3, it means I first rolled a 6 on the third roll, and so on. So the probability that X equals 6 is the probability that I will first roll a 6 on the 6th roll of the die. So we can just use the formula. It's really simple. The probability that x is equal to x, it's the probability you don't have success on the first x minus 1 rolls times the probability that you have success on the next roll. So what I mean by that in context of this question, the probability x equals 6 is the probability I don't get a 6 on the first 5 rolls, but then I do get a 6 on the next roll. And so the probability is 0.07, about a 7% chance that if I keep rolling a die, I won't get a 6 until the 6th roll. So I've also got some formula for the expected value and variance of x when x is geometric. So the expected value of x is just 1 over p. In this case, the probability of success is a 6th. The probability I roll a 6 on each roll of the die is 1 over 6. And that just equals 6. That kind of makes sense, that I would expect that I'll need 6 rolls in order to get the first 6. So the variance of x here, we didn't calculate the variance of the hypergeometric distribution because it's a bit too complicated, but the formula is really simple for geometric. It would just be 1 minus p over p squared. And that gives us 30. So, of course, if I wanted the standard deviation of x, it would just be the square root of 30. And that's pretty close to 5.5. And so that's sort of the average distance from the mean I would expect. If I performed this experiment over and over again, sort of the average distance from the mean, the average distance from this expected value of 6 would be 5.5. All right, thank you so much for tuning into this video. Best of luck studying, but you'll be right, you're a superstar. This has been the luckiest maths teacher in the world. Have a great day.